We begin lecture 48, and time permitting we will extend it for the additional hour for as the makeup for what we should have missed on what we missed on Saturday. What we will cover today would be probably the heart of a CDMA system. We have talked about multipath environment, so now we are going to go into the multi-user environment. Once having understood multi-user environment, we will talk about the impact. Why is power control so necessary for a CDMA system? And if you remember, when we talked about channel inversion, we said that there is a phenomenon called near-far problem. So today we will discuss the near-far problem and what that has on the CDMA system capacity. And in digital communications, we do study a section called optimum receivers. And I hope you will be able to really put all of the understanding of optimum receivers in our discussion on CDMA, because this gives us a very rich framework on which to understand and reinforce what you would have studied for optimum receivers. So that's the scope of today's two lectures. Let's quickly run through. So the quick summary of lecture 47. Lecture 47, we were focusing primarily on the multipath environment. So when it comes to multipath, always remember that we are working with a chip-spaced equivalent channel. So the received signal R of t is a summation of L plus 1 copies of different signals that have been spaced at chip duration. L t minus LTC. Okay, so this is a very useful form for you to remember, and of course there is the impairment Z of t. So the multipath components themselves did not occur at chip spacing. They occurred at arbitrary spacing, but you have been able to obtain an equivalent channel which behaves very similar to what was your true channel. Okay. So the characteristics of our channel are that we have included L plus 1 taps in the channel. This also led us to have L plus 1 taps in the rake receiver. So the rake receiver is usually correlated to the number of dominant taps, and for us, since we are working with a chip space model, it's for each of those spaces. The output or the decision statistic was obtained by combining the output of the different branches of the rake receiver. So there are L plus 1 copies of the signal that we are combining using the conjugate of the chip space channel, HL conjugate YL. Okay, this is what gives us the expression that we are looking for. So this basically gives us B times root EB summation L equal to 0 through uppercase L mod HL squared plus summation L equal to 0 through L HL star NL. Okay, so that is our expression that we have obtained, and this is how we got. So we did this for the for the first branch. Basically, we did note that the components of the signal of the noise can be characterized. So basically, expected value of eta L squared. This was N naught, white noise. But if you look at the output of the correlator, there is some component which is related to the cross correlation or the autocorrelation at different lags. So expected value of NL squared, one is eta, the other one is L. So this will be N naught plus EB divided by Q summation L is equal to 0 through L minus 1. Let me just do it a little bit differently. Okay. So this will be j equal to 0 through L not equal to L mod h of j squared, and this is the term that we were going to neglect under the argument that q is large. The upper L is small compared to q. So q, if q is large. Okay, so that's the summary of the rake receiver. Basically, this is the form that we had looked at. There are L plus 1 taps, and basically each of those taps gave us went through a correlation based receiver, which is multiplied by G star and then followed by an integration, then the corresponding coefficients added together. The observation that we made was that this block which is within the blue in each of those branches, because this is a linear operation, can be moved after the summation, in which case we get a structure which is a structure where the first part, where you have the delay chain followed by HL conjugate, HL minus 1 conjugate, that is a match filter to the channel. So first part is so when you after you have moved the correlation and integration outside, what you have is a match filter to the channel first, followed by a match filter to the chip waveform. So basically you have matched to the channel and to the waveform, and you have been able to get a decision statistic in which we have shown that there is the diversity benefit is present in the system. Okay, so that's a quick summary of the multipath, way we handle multipath, and several things that will become as you read and go through the expressions, you will see that yes, we have made some approximations. Almost all of the approximations will rely on the fact that Q is large, and once you have that, these approximations are reasonable. Let us move from the multipath environment to the focus on multi-user environment. I've just added a little bit more information to the figure that we had in the last lecture. Each user is spread by a corresponding waveform, user 1 by G1, user 2 by G2, and user k by Gk. These alpha k's, you can think of them as power control. Basically, you can adjust the amplitude of the signal. As they go through the channel, right, they could encounter different delays, because this is like the uplink. If the user 1 transmits slightly differently from user 2, or if the distance of user 1 is very different from user 2, there will be a difference in the delays in which when they arrive at the base station. So to account for that, we have included these delays. We have made the assumption that the channel is a flat fading channel. So the channel is a flat fading channel, so which means that there is no dispersion, but there can be a channel gain, and that channel gain is captured in terms of a complex constant. So in principle, this alpha and this could be combined to reflect a single coefficient. So you have the transmitted signal multiplied by a complex gain, which is because the channel gave you gain or you did power control, does not matter. You can combine them into a single complex gain. Now each of the users transmits their signal, and the signal encounters this channel. Now at the base station, I am listening to all the signals, because all of them are using the same frequency. So in other words, in the channel, these different multi-user signals get combined. So this is what is my channel. The channel basically combines all the individual user signals, and of course then will add some additive noise, and that is the composite signal that is given to the receiver. So the task at the receiver is to be able to detect any one of the k users that who have transmitted the signal. And so the assumptions once more, it's a flat fading channel. So R of t can be written as summation k equal to 1 to k users, alpha k uk. Uk is the transmitted signal. Transmitted signal depends on the bit at that instant of time, the energy level with which you are transmitting. Gk is the spreading waveform, and then Gk itself is described in terms of the chip waveform. Okay. So, alpha k can be treated as a combination of channel gain and the power control. Okay. So, that is a reference point, and we said, I believe we came to the point of writing down the decision statistic. If I want to pick up user 1 signal, I will correlate with G1 star of t and integrate 0 to t, and that gives me a decision statistic which gives a combination of the desired signal alpha 1 b1 root EB plus the noise filtered through the z of t filtered through G1 star of t plus the other terms that are present because other user signals are also there. So, R1k is the cross correlation between Gk and G1 star. So, similarly you can get for all the different terms. So, this is the multi-user interference part. So, your decision statistic contains that part that would have been there if it was a single user present, plus some other impairment that is part of the multi-user interference. Okay. So, this is the framework, and I believe we went through and justified that the expressions that we will get are of this form. But let me just pick it up from here and develop it in today's lecture. So, this is where we begin today's discussion. So, our key goal is to characterize multi-user interference, MUI. And if you look at the Rappaport's book, Rappaport, it is in the appendix, it says that this impairment or this presence of large number of users makes the multi-user interference appear Gaussian, and the argument is via central limit theorem, okay, via central limit theorem. And so, what we would like to understand today is how is this multi-user interference going to affect my performance of my system, what are some of the aspects, and we want to, so here is the way we would like to understand it. So, supposing we were given the bit transmitted by user 1 for a given B1, that means the bit transmitted by user 1, the expected value of y, the decision statistic given B1, that is I know B1, and given that this turns out to be alpha 1 root EB times B1, because I know that that is the signal that is being transmitted, plus this is the mean value. So, if you recall, whenever you did the digital communications, if you are transmitting a +1, your mean value will be +1 with some Gaussian noise around it. Similarly, if you are transmitting a -1, there will be some Gaussian noise. So, there is a mean value and a Gaussian. So, basically what we are going to do is make a equivalent understanding where there is a mean value which is represented by the bit that was transmitted. There is a noise that is present because of the Gaussian noise, and because our multi-user interference also happens to look Gaussian. So, we are going to draw it in this fashion. It is as if you had a Gaussian noise of slightly larger variance. Okay. So, basically that is the impact, or at least a way to start to visualize the multi-user interference. So, the multi-user interference, expected value of y given B1, this would be expected value of eta 1 plus expected value of root EB summation k equal to 2 to uppercase K alpha k bk R1k. So, this is the mean value. Okay. So, basically what we can show is that this expectation is of noise which will go to 0. This will be an expected value of bk's are expected value of bk equal to 0. So, this term also goes to 0. So, the mean value is just like before. It is, if you transmit it a +1, it will be +1, -1, -1, that is the mean value. Now, Another important extension to this picture is what is the variance. So the mean value is given by the bit value, but what is the variance? And that's what is going to be the spread of this red signal. So sigma y squared is the variance of the output of the correlator for user 1. This is given by expected value of y minus expected value of y magnitude squared. Okay. So expected value of y given B1 is alpha 1 root EB B1. So if I now write it down as y minus this thing, only the noise terms will be present. So this will be equal to expected, the signal part gets cancelled. What will be present is magnitude of eta 1 plus square root of EB summation k equal to 2 to uppercase k alpha k bk r 1k magnitude squared. Okay. So like before, expand this summation. This will be expected value of the whatever is the quantity within the bracket multiplied by its conjugate. So the first term is mod eta 1 squared. Second one is the term with the conjugate of itself. So it will be root EB gives me EB summation k equal to 2 to uppercase k alpha k bk r 1k summation m equal to 2 to uppercase k alpha m conjugate bm conjugate r1m conjugate, okay, plus then you have 2 times the real part of eta 1 conjugate root EB, again it is just expanding out this term, summation k equal to 2 to uppercase k alpha k bk r 1k. And keep in mind that there is an expectation outside. Okay. So the first one is the noise term AWGN. So the first term will be given by the noise variance N naught. Okay. Now expected value of Bk Bm star, if k is not equal to m, these will be independent and they are 0 mean, so that term will cancel. So what will be left with is only when k and m are the same. So it will be EB summation, just a single summation now, k equal to 2 to uppercase k alpha k mod squared expected value of R1 k magnitude squared. Okay. Beta squared will b squared will be equal to plus 1, and of course this term will also go to 0 because you get expected value of bk. So this is a very important equation. I just want you to sort of pay attention to it. What is it that we have done? We have taken the multi-user signal, correlated with the waveform of user 1, applied the as if you were followed by the integrator, and you got a decision statistic. The mean value is given in the previous equation, the variance of the decision statistic is given. So this is more or less going to be a foundational equation for us in our analysis. An expected value of R of 1 over k, R1k, this is approximately 1 over q. That's how we would design the codes, and that would be the case when you had the PN sequences. So this expression is a very key expression for us. So which is sigma y squared is equal to n naught plus EB divided by q summation k equal to 2 to uppercase k mod alpha k squared. Okay. So that's the variance of the decision statistic. Now we get into the very interesting parts of this discussion. So this is a CDMA system where we do fast power control, and so we will pick up several of these key concepts that we have discussed earlier. So this is the uplink. So the mobiles are transmitting to the base station, mobile to the base station, and the base station is the one that controls the transmit power. So it controls the, so we have fast power control. So since it is the uplink, mobile power is controlled depending upon the system. CDMA 2000, it is 800 times per second, 1500 times per second for wideband CDMA. So we can call it fast power control for both of the systems that we are familiar with. Okay. Now, a very key concept. What is the role of power control? It is to make sure that all the users reach the base station with approximately same power. Okay. So at least notionally, we want all the alpha k's to be equal to a constant. All of them to be the same constant, right? Only then that's what tells you that all of them are being received at the same time. So this is for all values of k. Okay. And without loss of generality, we can take that constant to be equal to 1. Okay. Just since you can choose what that constant is, all of them to be equal to 1. So now comes a very interesting observation. Sigma y squared is given by n naught plus EB by Q into k minus 1. Okay. So basically there are k minus 1 interfering terms, and each of them contributes EB by Q. Okay. So now comes the calculation, interesting calculation of SINR. What is the signal to interference plus noise ratio? EB is the signal component. The noise component, after I have taken out the mean value, this is the noise component. So this is given by N naught plus EB divided by Q into K minus 1. Okay. Another interesting form of this equation, divide numerator and denominator by N naught, EB by N naught divided by 1 plus 1 over Q EB by N naught into K minus 1. Okay. Very interesting form, because what it says is EB by N naught, what would have been a single user's SINR, right? A single user's signal to noise ratio. But now, because other users are present, though they have been suppressed by our spreading factor Q, they are still present, they are contributing to the, so the denominator is a number that is greater than 1. So this is going to take you away from the performance of a single user system, and by how much is it going to take you away is called a degradation parameter. So if you call this as 1, the degradation parameter is this quantity dg, degradation parameter, and this is typically less than, worst case it will be equal to 1, best case it will be equal to 1, always mostly it is less than 1. Okay. What are the things that affect dg? So if the multi-user interference goes up, what does that mean? Basically this EB by Q into K minus 1. When will multi-user interference go up? If K goes up. If K goes up, what happens to DG? DG goes down, becomes smaller. So that means your effective SINR is going to become smaller. So again, you can see the relationship between the number of users, your spreading factor. If you reduce your spreading factor, what will happen? You will hurt yourself again, because the degradation parameter is going to become smaller. So all those things can be understood in this fashion. Okay, so here is a couple of points regarding the multiple user interference, multi-user interference, MUI. MUI, the mean value is 0. It's a 0 mean, basically that's what we have shown, and the variance sigma squared of MUI is given by this quantity, which is K minus 1 EB divided by Q. Okay, because the other one is the AWGN component, this is the multi-user variance component. So this is what we would like to think of as our equivalent model. So, if you go back to our model, where did we draw that? So, the wider variance is now caused by the presence of the multi-user interference, and the expressions for the interference have been given as follows. The original variance with only the AWGN plus the multi-user interference. The multi-user interference component can be captured in this form. Okay. So, it is a zero mean and it is Gaussian in nature, and it has got a certain variance that depends on the number of users. It depends on your inversely proportional to your spreading factor. Smaller the Q, larger the variance, and therefore, I want you to start thinking along these lines. Okay. Now, a couple of points to sort of set the context very clearly. So, compare this with a narrowband system. Okay. Compare this with a narrowband system such as GSM. Narrowband systems such as GSM. Now, what can you tell me about the interference that you will see in a GSM system? You see interference from a co-channel cell. It is not from your own cell. It is coming from somebody else who is using the same frequency. Now, if I look at tier 1 users, what is the maximum number of co-channel cells? 6. So, it is still a small number. So, the single narrowband system, the interference has got a very different characteristic. Interference comes from 6 tier 1 users at most, tier 1 users, okay, and the interference still, though there are 6 of them, it still looks like a GSM signal. So, the way we characterize that, we say that the interference is like colored noise. It is got a strong spectral shape which looks like the GSM signal. Okay. It is colored noise. So, the interference management in a GSM system has to keep in mind that the interference moves away. Once it becomes an interference dominated system, it moves away from AWGN, it moves into a noise which looks highly colored. Okay. It has got a strong spectral shape. On the other hand, if you move over to the CDMA system, what are we saying? We have large number of users in the system. The multi-user interference now looks Gaussian, and therefore, our ability to work with this interference is somewhat different. Okay? So, the impairment in this case behaves like white noise or manifests itself like white noise. Impairment as white noise. Okay? The reason for this is that we have a large number of users, and then central limit theorem kicks in, and then we are able to make the argument, large number of users. Okay, I will just say K up with an up arrow, large number of users, and also the fact that the spreading factor plays a role. Spreading factor plays a role in the larger the spreading factor, the presence, the spreading factor also has a role to play. Okay. Now, think very carefully. I have a CDMA system with 32 users in the system, 32 users, just as an example. Okay? Example. So, it is a CDMA system, 32 users, uplink, talking about uplink. I am the base station, I want to detect user 1. How many interfering signals are present? How many interfering signals are present? 31. 31, correct? Okay, very good. So, 31 interfering signals are present. Now, think and answer this question. I have changed it to the downlink. Okay, if 32 users are in the system, how many signals is the base station transmitting? 32. Okay, how many interferences? I am mobile now, receiving from the base station is transmitting 32 signals, 32 user signals. How many interfering signals do I see? 31 user signals, but base station transmits something else also. It transmits control information, it transmits a pilot channel, it transmits, at the end of the day, anything that is not my user signal, the pilot channel is actually useful for me. I use it to do channel estimation, but when I want to detect my user signal, what happens? It is actually interference to me. So, in the downlink, you have to keep in mind that it is 31 plus other channels, right? Whatever thing the base station is transmitting is going to cause interference to me. In addition, other base stations transmitting also are going to cause interference to me. So, in a CDMA system, the role of interference is something that we really have to get our hands on. Yes, it looks Gaussian, but at the end of the day, you've got lots of sources of interference which you want to be careful about and be able to manage and control. Okay. So, this is our starting point in terms of our entry into the multi-user system. Any questions regarding the points that we have mentioned? So, because I just want to be sure that we are clear on this, and then we build on this in the next few minutes. Okay. Any questions on the multi-user part? K users, each one has got a different spreading factor. There is this alpha coefficient which corresponds to power control plus channel gain, and basically if I do proper power control, all these signals will arrive at the base station with the same power level, and which then tells me that I can characterize my noise in the following way: signal EB divided by N naught, which is AWGN, and then the other terms, assuming ideal power control, will be EB by Q into K minus 1. And that can be related to a degradation factor, which then tells me that my EB by N naught will always be worse than what I will see in just a single user AWGN channel. Okay? Any questions? Okay. Now we want to spend a few minutes on intuition, because the intuition helps us in building up the. So here is a very qualitative perspective. Okay. This is frequency. AWGN I always will show like this. So this is the noise floor. Okay. Noise floor. Now what happens in a CDMA system, direct sequence spread spectrum? You transmit, you take a narrowband signal and then you spread it. So basically the noise looks like it became slightly higher because you spread the signal. At the receiver, what do? We despread this signal. The despread signal looks like this. My SNR is with respect to the noise floor, only one. So this becomes my signal to noise ratio. Spreading, despreading. What happens in spreading? What happens in despreading? Are you clear about this? Now move from this into a multi-user environment. Okay. I have a multi-user environment, noise floor like before, noise floor. Okay. Now I have user number 1. User number 1 is adding some increase in the noise floor, then user number 2 ... and then finally user K. Okay. So user 1 is noise floor, red is user number 1, green is user number 2, and purple is user K. So each of them have been spread. So this is my environment in which I am detecting my signal. Okay. Now if I detect red user number 1, like before, I despread my signal, others are not affected as part of the despreading process. Notice something has happened, some change has happened with respect to the previous figure. My threshold or difference with respect to the impairment is now no longer SNR, it is SINR, and it has become smaller. Noise plus interference is now higher in a CDMA system. But assuming that, so basically this level will be the level of noise plus K minus 1 interferers. That is the reference impairment level. Okay. So very important that I achieve this picture and understanding. Now I want you to think about a anomalous situation. Anomalous means things are not ordinary. So noise floor, user number 1, okay, and user number 2 is transmitting with more power than they need to. That is user number 2, all of the other users, user number 3, user number 4, user k. Okay, so basically there are lots of other users. The one anomalous user is the green user. Okay. Now, if I am detecting green, notice what will happen. Detecting green, the green part comes out of the noise floor, all the others settle down, he gets a pretty decent, if you take the others to be at this level, okay, gets a decent SINR. So, SINR of user 2. But what if I had to detect any of the other users? What is the situation with the other users? Let us say I want to detect the red one. The red one is here. The noise floor because of the green is much higher, and effectively the SINR of user 1 is actually quite bad compared to SINR of user 2. User 2 is quite happy because he does not see any problem, he just he is detecting a signal, but the scenario is that SINR 1 for all the other users other than user 2 are getting affected. So, keep in mind that this is our starting point to understand the complexities of a CDMA system, how one user's signal actually causes interference to others, and it can cause interference in ways that are very, very detrimental to the overall system. Okay. So, now another thing that you will be able to appreciate from this sort of this qualitative figure is that if I start adding more and more users, eventually I will reach a point where I cannot detect my signal. Okay. So, there is a capacity understanding that comes from the interference floor. There is another capacity perspective that you get from looking at this mismatched power. If one user is transmitting with a lot of power, he is going to kill the capacity of the system, and therefore, we need to be careful with that. So, this is a way to start thinking in terms of CDMA capacity, but we are going to formalize this in a short while, but I wanted you to sort of start thinking in terms of the multi-user and its impact. Any questions on the multi-user part that we have just now discussed? Okay, if not, we will move quickly into the next part of our understanding, and we will try to build on the multi-user environment. But before we go there, I just want to quickly summarize the results that we have obtained so far. Okay, so the presence of multi-users depends on the number of users, it depends on your spreading factor. We assume that the impairment is Gaussian in nature, and therefore we are able to characterize it, we are able to work with that. Okay. So, now I want to give you a reference point that is used quite often in a CDMA system. So, performance in a multi-user environment, performance in multi-user environment. Few comments about that, and then we move into the capacity discussion. Multi-user environment. So, the first one is if k equal to 1, number of users equal to 1, direct sequence spread spectrum performance is same as a AWGN flat fading channel, same as AWGN or flat fading. There is no gain that you get for a single user system. Okay. This is a point that we had made very early in our discussion. Okay. The second aspect is spreading and despreading, they cancel each other, that is they are the inverse operations. So, spreading and despreading are inverse operations. So, as far as the signal is concerned, the signal comes back to its narrowband form. Spreading and despreading, I will just say cancel each other, but please interpret it as the inverse operations cancel each other as far as the signal is concerned, cancel each other, but it does not do anything to the noise. Okay. So, it does not do, so the AWGN variance AWGN variance is not affected, not changed. So, if it was N naught in the narrowband system, it is going to be N naught in the CDMA system as well. Okay. So, then what is the interest in a multi-user environment? So, the main focus for the direct sequence spread spectrum is the capacity. What are the benefits that we can get in terms of the capacity via the multi-user interference suppression because of my spreading process and the receiver techniques that I do. And of course, there is a performance gain if I have dispersive channels, performance gain because of multipath resolution. Okay, so that is why we are interested in direct sequence spread spectrum, because it gives you multipath resolution and rake receiver will combine it, giving you a form of diversity. So, the combination are that I have spreading, which will help me work with multi-user interference. Because it is a spread spectrum wideband signal, I get the benefits of diversity. Okay. So, here is probably the most important statement. If my spreading codes are perfect, that means they are perfect in terms of mutual orthogonality and self orthogonality, then what we will achieve is called a single user bound. Okay. What that means is because the codes are perfect, what I will achieve looks like a single user. The performance of other users is not visible at all. BER versus SINR, I will get the performance of a single user. It will look like what this is like k equal, look like k equal to 1. Though k is not equal to 1, this is what it will look like. This is the BER that you will get. On the other hand, if I do not have perfect codes, then what I will see is a slight degradation when there are 2 users. Then this degradation will become even more when it becomes 3 users. Then eventually it starts to become worse and worse because of the presence of multi-user interference. Okay, so the BER graphs will increase as k increases for non-ideal codes, which is what all practical systems will have. Our PN codes, M sequences scrambled, are they ideal codes, perfect codes? No. They do have some leakage that will come in. So, all of our CDMA systems will have this. So, whenever you look at the performance in a CDMA system, multi-user environment, you will always talk about a single user bound, because you always want to see how far off are you from the single user bound. The closer you get to single user bound, the better is your system, and therefore how well you have designed your system. So, single user bound serves as a reference for us for any of our discussions. Let me also tie in together the near-far problem and help put a context to the situation that we discussed. Okay. So, when there are k users in the system, then we know that the multi-user interference, the variance of that, okay, this will be given by N naught, multi-user interference seen by ith user. Okay, is N naught plus 1 over q summation k equal to 1 through uppercase k, but k is not equal to I, because I is the desired user, everyone other than I is ek mod alpha k whole square. Okay. We will make one assumption just to get the insight from this particular. So, we will assume that the EB with which we want to transmit each of the signals is the same. Ek is equal to EB for all values of k. That is, each of the signal constellations are all normalized. All of them are transmitting the same value. So, under this assumption, with perfect power control, we already know the answer. With perfect power control, we will have mod alpha k equal to 1 for all values of k, and my multi-user interference seen by the ith user is the same as the multi-user seen by each of the others, given by n naught plus 1 by q into k minus 1 into EB. Okay. Now, just for you to have a feel for the practical impact, when a base station is receiving in a CDMA system is receiving without power control, that is one user is close to the base station, one user is far away from the base station, the dynamic range can be as much as 90 dB, 90 dB. So, the range of signals is approximately 90 dB. So, your power control range is actually in a 90 dB range. You can ask somebody to go up by some amount, come down, the total dynamic range of your power control is very, very large. Now, when you have a practical system, power control may not be perfect. So, with power control errors, how is it going to manifest? It is going to manifest saying that all alpha k's equal to 1, that assumption does not hold. Okay, and that is going to be the practical understanding of the situation. Okay. Now, how does it affect the SINR of each user if power control is not, so SINR 1, that is of user 1, how does that look like? So, the SINR of user 1 will be mod alpha 1 squared EB, notice that it is not equal to 1, so I cannot EB by n naught multiplied by dg1, whatever is the degradation that is going to be caused by the multi-user interference. Okay. So, that is the so dg1 will be expression for that will be 1 plus EB by n naught 1 over q mod alpha 1 squared summation k equal to 2 to uppercase k alpha k by alpha 1 magnitude squared. So, basically I have rewritten the previous expression with the alpha k's present, and I have just written it so that we can bring in explicitly the expressions for alpha k's. Okay, and there is a minus 1 by the way. This is the term in the denominator. Okay. Now, the key step is how do we interpret and how do we understand. So, let us take a simpler case, keep that equation in your in view, and please look at it in the following special case. Okay, I am going to look at a special case of 2 users. Okay, 2 users. The special case of 2 users where alpha 2 is much larger than alpha 1. That means user 2 is transmitting with more power than he needs to. Okay, so, basically either he is very close to the base station or he has not reduced his power, something alpha 2 is much stronger than alpha 1. So, degradation seen by user 1 will be 1 plus mod alpha 1 squared EB by n naught 1 by q, since there is only 2 users, it will be alpha 2 by alpha 1 magnitude squared, alpha 2 by alpha 1 magnitude squared. Okay. So, this can be written as 1 plus 1 over q EB by n naught mod alpha 2 squared inverse. Okay. So, if alpha 2 is much larger than alpha 1, the degradation of SINR 1 is going to be much more significant than a degradation of SINR 2. So, you can write down the degradation of SINR 2, this will be 1 plus 1 over q EB by n naught mod alpha 1 squared inverse. Okay. And now, if you extend this to more than 2 users also, the trend will follow. Alpha 2, because it is in if you write down the degradation for DG2, alpha 2 will come in the denominator. So it will dominate, it will suppress the others. So the DG2 becomes a quantity that is not significant, does not affect the SINR much, but all the other DGs will affect the users. So if you now link this to the scenario that we just now drew, I will just redraw that for reference. This is noise. This is a 2 user case. User 1 is transmitting with a lot of power. This is user 1 and user 2 is right there, user 2 power level. Okay. Now when I despread user 1, despread user 1, user 2 is sorry, if when I despread user 2, then what I have is, this is my SINR for user 2. Well, user 2 is stronger. So I think I have labeled it wrong. Okay, user 2 is stronger. So this is user 2, and let me draw user 1 here, user 1. Okay, so when I try to despread user 1, this is my SINR of user 1. On the other hand, when I try to despread user 2, you will notice that it is a very different situation. Noise is there, user 2 is there, this is user 1. If I remove user 2 from the picture, user 1 moves over here, the blue signal gets despread, the SINR is sitting here, SINR of user 2. Okay. Now if SINR, if user 2 increases its power even more, who is going to get hurt? User 1 is going to get hurt, user 2 is not going to get hurt, user 2 is quite happy. So this is one of the reasons why this, this power control is so important, and this is precisely what we call as the near-far problem. Near-far problem. Okay, a user, in this case you can think of user 2 as a near user who is transmitting with a lot of power, and because of user 2, user 1 is getting affected, and it may come to a point where user 1 cannot even be detected. So a near user who is transmitting with more power than he needs to will affect the detection of a user who is further away and therefore unable to communicate with the base station. Okay. It is tied to the notion or understanding of interference and power levels and spreading and despreading, all of that put together. But where does it actually creep in? When all of them are under ideal power control, it does not show up. But when one of the users does not obey power control, then it starts to affect all of the others except the one user who is not obeying power control. Okay? This is probably one of the most important questions that you will need to answer. How do you jam a CDMA base station? How do you jam, how can you jam? Based on what we have discussed now, you know the answer. Jam a CDMA base station. How do you do that? Go close to the base station and transmit with full power. Nobody else will be able to communicate. It's that simple. And that is why they are so careful about power control in a CDMA system. Whether it's illegal, don't try that because you will go to jail. Because but the thing is, it's as simple as that. If you go close to the CDMA base station and you transmit with full power, everybody else is wiped out. And what is it due to? Near-far problem. That's it. And nothing else you can do. Nobody, none of the other people can do anything about what they are seeing. Okay, so we are at a very interesting point where from here getting to CDMA capacity is just one step. We will do that and then talk a little bit about the optimum receivers and then conclude. Thank you.